The General Theory of Relativity, GR, is one of the two pillars of Albert Einstein's theory of relativity, the other being the Special Theory of Relativity, Senior. General relativity is a theory of gravitation and space-time that was first published by Einstein in 1915. It replaced Isaac Newton's theory of gravity and has since become a fundamental framework for understanding the nature of gravity and the geometry of the universe. Here's a detailed explanation of the key principles and concepts of general relativity. 1. Principle of equivalence. At the heart of general relativity is the principle of equivalence, which states that locally, within small regions of space and time, the effects of gravity are indistinguishable from the effects of acceleration. In other words, if you are inside a sealed, windowless room and cannot see the outside, there is no experiment you can perform to determine whether you are in a gravitational field or if the room is accelerating in empty space. 2. Space-time as a fabric. In general relativity, space and time are combined into a single four-dimensional continuum called space-time. Einstein's theory describes how the presence of mass and energy warps or curves the fabric of space-time, causing objects to move on curved paths. This curvature of space-time is what we perceive as gravity. 3. Einstein's field equations. The fundamental equations of general relativity are known as Einstein's field equations. They describe the relationship between the curvature of spacetime, represented by the metric tensor, and the distribution of matter and energy in the universe. The field equations can be written as Gmn equals 8 pi Gtmn, where Gmn is the Einstein tensor, Tmn is the energy momentum tensor, G is the gravitational constant, and c is the speed of light. These equations relate the geometry of spacetime, on the left side, to the presence of matter and energy, on the right side. 4. Curvature of spacetime. Massive objects like planets, stars, and black holes cause a curvature in the spacetime around them. Objects in freefall, like a satellite orbiting a planet, follow the curved paths, called geodesics, determined by this curvature. This is what we perceive as the gravitational force. It's important to note that, in general relativity, gravity is not a force in the traditional sense but rather the result of curved spacetime. 5. Gravitational time dilation. General relativity predicts that time runs slower in stronger gravitational fields. This phenomenon is known as gravitational time dilation. It has been experimentally confirmed through precise measurements of time on Earth and in space using atomic clocks. For example, clocks on GPS satellites run slightly faster than clocks on Earth's surface due to the weaker gravitational field in orbit. 6. Predictions and tests. General relativity has made several predictions that have been confirmed through experiments and observations. These include the bending of light by gravity, gravitational lensing, the precession of the orbit of Mercury, and the existence of black holes. 7. Cosmological implications. General relativity plays a central role in modern cosmology. It forms the basis for our understanding of the expansion of the universe, the Big Bang theory, and the concept of dark energy. 8. Gravitational waves. General relativity predicts the existence of gravitational waves, ripples in space-time caused by accelerating massive objects. These waves were first directly detected in 2015, confirming another prediction of Einstein's theory. In summary, the general theory of relativity revolutionized our understanding of gravity, replacing Newton's concept of a force with a description of gravity as the curvature of space-time caused by the presence of mass and energy. It has been confirmed by numerous experiments and observations and remains one of the foundational theories of modern physics.